Hello, everyone. I hope you can hear me clearly. I'm here to make a record for you since we canceled the class on Thursday. So I need to do the virtual makeup class. Otherwise, I cannot finish the content that I want to cover. So let's get started. Last time we finished here, right? We talked about the key difference between the fitting line, which is here, the solid line, the difference between the fitting line and the true population regression function, which is dashed, okay? We talk about what is it, okay? It's our estimate from the sample, and it's the true relationship. And do we know it? For fitting line, for the fitting regression, yes, we calculated it, right? Because we calculate. So we know it. But for the PRF, we don't know, we never observable. The third question, does it change for the fitting line? Yes, because different sample, different lines. But for the PRF, no, it's fixed in the population, okay? It's fixed in the population. So let's continue. Next one, I want to show you the examples, okay? This is the real example. It's about wage and education. This one is very close to your own life, okay? So let's think about it. What is the question? What is the question that we are trying to answer? Okay, the question is, does staying school longer actually make you earn more? Okay, so let me write it down. Does staying school longer actually make you earn more? Okay, this is our question that we want to answer. So here we have our y, which is hourly wage. Y equal beta 0 plus beta 1 education. Okay, so education here is year of education plus mu. Okay, other factors. What can we have in the mu? For example, the mu, maybe it contains experience, right? And also the talent. Maybe sometimes luck, etc. So the OLS result from the real data is the fitted regression, which had equal negative 0.9 plus 0.5 for education. Let's read each number. So for this one, this is beta 1 hat. What does it mean? It equals to 0.54. That means in the sample, one more year of education was associated with an increase in hourly wage by $0.54. Or one more year of education, you earn $0.54 more per hour, okay? How about this one? Negative 0.9. This is our beta 0 hat. It's negative means that Of course, it's our intercept, right? And here it's negative. So it means that someone with 0 year of education earns negative $0.9 per hour. Does it make sense? What do you think? So actually, this makes no sense in real life, but don't worry. The intercept is just a math anchor for the line, okay? Because it means when should the line start. So here, the intercept is a math anchor of the line. So we never actually have people with 0 years of education in this sample. So don't interpret it literally. Next question, causal interpretation. Can we explain our beta 1 hat as the causal inference, the causal interpretation? What do you think? So same problem as before, okay? Because mu here, okay, because mu here, our error term here contains intelligence, family background, motivation, all of those probably related to education level, okay? So it means that the condition expectation of mu given x here doesn't equal 0. That means beta 1 hat equals 0.54. It's biased, okay? Here biased means that it's not purely causal effect, okay? Let me show you before. Here, the same. It's not purely causal interpretation. So the true causal effect of education alone is probably smaller. We also can see it. Each extra year of school predict positive $0.54 per hour, but whether school itself causes this or smarter people just study longer, we cannot tell from OLS alone. Next example, okay, one more example. This time is about politics. So let's take a look at this example. What is the question here? Okay, we have share A, percentage of campaign expenditures, candidate A. We have vote, percentage of vote for candidate A, okay? So the question might be, if a candidate spends more money on their campaign, do they get more votes? Okay, if candidate spends more money on their campaign, do they get more votes? The question is very important, as I mentioned earlier, okay? Your research always starts with the question, okay? The question that you want to answer, the question that you is interested in. So here we have, if the candidate spent more money, okay, more expenditure on their campaign, do they get more votes? Okay, so here is related to this example. And why here is the vote A, percentage of votes candidate A receives we have beta 0 plus beta 1 as usual. We have share A. So here's our x and plus mu. So think about it. What can we have in our error term mu here? So mu here may be candidate's popularity, okay? And scandal or the party reputation, okay? The party from the candidate. Party here means political party, okay? Reputation or economic conditions, etc. So the OLS results shows that beta 1 equal 0.464. This is beta 1 hat. It means that if candidate A's share of spending increases by 1 percentage point, he or she receives 0.464 percentage points more of the total vote, okay? So here means, in a simple way, if X goes up 1%, Y, because it's positive, okay? So Y increases, okay? How many percent? Okay, so here if X goes up 1%, Y goes up 0.464%. Okay, and here beta 0 hat, okay, which is 26.81. This means that if candidate A spends 0% of total campaign money, predicted to get 26.81% of votes. That means this still gets some votes just from party loyalty, name recognition, etc. Okay? Same here, causal interpretation. Does spending more cause more votes? Or do popular candidates attract more donations and win more votes? Maybe, right? Maybe we have a popular candidate and then the donors give more money, so they get higher shares, eh? Of course, they're gonna get more votes. So mu includes candidate popularity, which is related to share A. So here the same, our condition doesn't hold, okay, doesn't equal 0, okay? So that means the causation is unclear. Now let's take a look at some guaranteed properties of OLS, okay? Things that are always true no matter what data you use, okay? Property of OLS means that things that are always true. The first one, two definitions you already know. So we have y, we have a yi hat equal beta 0 hat plus beta 1 hat xi. Here is our fitted value. And then we have mu I hat equal the true y minus the fitted y, okay? This is our residual. Nothing new here, okay? So we saw this before. So here we have our fitted or predicted value y I hat, and here is mu I hat, or the deviations from regression line residual. Now, three algebraic properties of OLS. The first one, property 1, deviations from regression line sum up to 0. What does it mean? It means that all residuals add up to 0. The second, property 2, covariance between deviations and regressors is 0, okay? This is the deviation, and xi is our regressor. Okay, the covariance between deviations and regressors is 0. In other words, x and the residuals are uncorrelated, okay? X and the mu hat are uncorrelated. Property 3, the regression, okay, here is the average, okay, the expectation of y, sample averages of y and x line on regression line, okay, we have a sample average of y and x. So the line on regression line, it means that the regression line always passes through the point x bar, y bar, okay, the average, or the OLS line always goes through the center of your data, okay, always. These three properties are not assumptions, okay? So remember, they are not assumptions. They are mathematically guaranteed. Every time you run OLS, the line is always balanced, always centered. Let's take a look at the table here. So here is about fitted values and residuals from the first 15 CEOs, okay, our example before. So here is ROE is our XI, and salary is YI. So XI and YI is our data, is our sample, right? And then here salary hat, which means YI hat. Salary hat, for example, here we have, so this point means YI hat equal beta 0 hat plus beta 1 hat times XI. And we have mu hat here, okay? The residuals, right? Those columns are the residuals, okay? You can see some is negative, some are positive. So here is mu I hat equal the true y minus the fitted y. For example, here, CEO number 12 Okay, CEO number 12. 12 salary was $526.023, lower than predicted using the information on his firm's return on equity. Okay, lower. Okay, so we have our OLS line, but now a natural question. How good is our line? Does X actually explain Y well? Okay, so here is the question. How good is our line? Does X actually explain Y well? This is called goodness of fit, okay? The big idea is that variation, okay? The big idea is about variation. Think about wages. People earn different amounts, some high, some low. That's variations in Y. So our regression line tries to explain that variation using X, right? Because we try to use X to explain Y. So some variation explained by our line, but some variation still unexplained. That's mu. Let's take a look at the three measures. Let's learn the lambs first. The first one, SST means total sum of squares, okay? Represents total variations in the dependent variable, or how much does Y vary in total? So, okay, so you can see from the formula, okay, the true Y minus the average Y, okay? This means how much does Y vary in total. Next one, SSE, explained sum of square, represents variation explained by the regression. Or it means how much of that variation does our line explain? How much of that variation does our line explain? This is SSE, right? You see here, this is Y I had minus the average Y, okay? Means how much of that variation does our line explain? The next one, SSR, means residual sum of squares, okay, represents variation not explained by regression, okay, not explained. So, of course, it's related to our mu I hat squared. Here is how much variation is still unexplained. How much variation is still unexplained? Okay, so we have SST, total sum of squares, SSE, explained sum of squares, and SSR, residual sum of squares. Let's see the relationship or decomposition of total variation. And the relationship here is always true, okay? Total variation equal explained part plus unexplained part, okay, which means SST equal SSE plus SSR. Okay, so let me write it down. We have 3 parts, right? And what does it mean, or what is its meaning? And also, we want this to be what? Okay, first one, SST. Okay, total variation, it means total variation in Y. We want this to be fixed by data. And next part is E. This is explained by X. And we want this to be as large as possible, all right? We want to expand more. And then SSR, this is the unexplained, also residuals, right? Residuals, okay, or residuals. Of course, we want it as small as possible. This is the most famous numbers, okay? Next one, let's take a look at how we measure the goodness of feet, which is R squared. This is the most famous number in regression. Everyone use it. Let's understand it properly. Take a look at the formula. What does it mean? The formula in plain English, okay? Here, what fraction of the total variation in Y is explained by X? Okay, this is the formula in plain English. What fraction of total variation in Y is explained by X? Let me write it down to help you better understand. What fraction of the total variation? Okay, what fraction of the total variation in Y is explained by X? And also, R squared measures the fraction of the total variation that is explained by the regression. R is always between 0 and 1. Okay? If R squared equal 1, it means X explains everything. But this is not realistic, okay? Actually, the model that we want to use, can X explains everything for Y? Okay, so this is not realistic. This is perfect fit. Okay, perfect fit. That means every dot is on the line. Okay. Next one, suppose R squared equal half. It means that X explains 50% of variation. Okay, so if half, so means X explains 50% of variation. Another case, if R squared equals 0, it means X explains nothing. Here is a common mistake, okay? Suppose, okay, suppose we have R squared equals 0.9. What does it mean? It means X explains 90% of variation in Y, but causation still needs our condition, expectation mu given X equals 0, okay? So R squared only means that X, how much X explains Y, okay? It doesn't mean our model is correct. It doesn't mean the causality, okay? So this one, not, okay, maybe it doesn't mean causation. Because causation, we needs our conditions, okay? Higher R squared does not mean causation. It just means good fit, okay? Next one. Okay, so let me write it down here as well. Higher, okay, high R squared does not means causation. Okay, remember it. Please bear in mind. Next one. Okay, here is our example, right? So for the first example, CEO salaries and return on equity, the R square is 0.0132. It means that the regression explains only 1.3% of the total variation in salaries, okay? Because we need percentage, that means you move the decimal point here, so you get 1.3%. Next example, voting. Okay, voting outcomes and campaign expenditure. So here we have R squared equal 0.856, which means the regression explains 85.6% of the total variation in election outcomes, okay? I already mentioned here to you, a high R squared does not necessarily mean that the regression has a causal interpretation, okay? It only tells us how well does my line fit the data, okay? It says nothing about why the pattern exists, okay? R squared only tells you how well does my line fit the data. It doesn't guarantee a causal interpretation, okay? Let's continue. Let's see the semi-logarithmic form, okay? Semi-logarithmic form. It means that we put log only on y, and log here is the natural logarithm of wage, okay? It's the natural log. So here is our new model. Log wage equal beta 0 plus beta 1 education plus mu. So this changed the interpretation of the regression coefficient. Let's see how does the interpretation change. So here we have beta 1 equal the percentage change in wage and also the change in education, okay? Which means that if you rearrange it, 1 over wage times the change in wage over the change in education. And here we have in the numerator, this part is the numerator, is the percentage change of wage. In the denominator, it's the change for education only, okay? If years of education are increased by 1 year. Okay, so let me show you an example. Before, what is our beta 1 hat? Before, let's go back. Before, our beta 1 hat is here, right? Before our beta 1 hat, okay, without log, let me copy this one. Okay, here. Before beta 1 hat equal 0.54. Okay, and this is the dollar amount and it's fixed. But now we have 0.083. Okay, this is our new beta 1 hat. What does this mean? Okay, this wage increases by 8.3% for every additional year of education, okay, which means the return to another year of education. For example, let's see here. Because this is our estimated results, right? And then suppose we have $0.83 and then we divide it by $10. And also if one more year of education increases, okay, so we have 0.083, which is the same here. Okay. And then we need to transform it into percentage, okay? So it's gonna be positive 8.3%. And also This graph shows you the growth rate of wage is 8.3% per year of education. Okay. I think I need to summarize for you. Okay, so let me add page. So before linear model, what we have, linear model, beta 1 hat equals 0.54, right? And this means if one more year of education and the salary will increase by $0.54, okay, per hour. This is dollar amount and this is fixed. But right now we have log model, semi-log. So our beta 1 approximately, okay, equal to, because actually 0.083 it's very small. So let's say take the approximation. So it's approximately 0.1, right? And this means that plus 1 year of education, the same. But here you're gonna have 10% wage increase, okay? Here we talk about the percentage. So here is the percentage. It's not fixed dollar anymore. And another one, linear with log, semi-log. Okay, what is the form? And what does beta 1 hat mean? So for, I need to move this. Okay. One more line here. So for linear, it's look like this, okay? Which equal beta 0 plus beta 1 education plus mu. What does beta 1 mean? Okay, plus 1 year, and then you're gonna get beta 1 hat dollars, right? Be careful, the interpretation is very important at your level, okay? Because you have to interpret your estimation results later for your research exercise, which is 409. And next one, semi-log. So here's log wage, which is beta 0 plus beta 1 education plus mu. What does beta 1 mean hat? What does beta 1 hat mean here? Plus 1 more year gives you beta 1 hat times 100%. Okay? The explanation is different. So when the effect of x on y is better described as a percentage change rather than a fixed amount, okay? So you use log y. So beta 1 hat now means percentage, okay, not dollars anymore. Let's continue. Okay, we talk about log, semi-log. So now let's see log model here. So that means for both x and y, we take the natural logarithm, okay, on both of x and y. So here log y is the log of CEO salary, log x is the log of firm's total sales. So right now both sides are in log form now. And this form, it's very common, okay, in economics paper. We use this form all the time, okay, because as you may know, log function is concave, okay? Log function looks like this. It's concave, which means non-negative, okay? So suppose your data have some negative value. If we take natural log, we just avoid the non-negative value, okay? This is very useful and practical when we do the empirical research. So of course, that's gonna change the interpretation of the regression coefficient as well. Here means that if sales increase by 1%, how much will y increases, okay? How many percentage change of salary? So remember, logarithmic changes are always percentage changes, okay? So we have numerator here is the percentage change of salary, and new denominator here, okay, this is numerator, this is denominator, means sales increase by 1%. Okay, or let me write it down for you. If sales increase by 1%, CEO salary changes by beta 1 hat percent, right? And this is also called what? You learned this one from microeconomics. This is also called elasticity, right? This is also called elasticity. Okay, so let's see the example here. So we're gonna put real numbers into the log model. Okay, the result, beta 1 hat equals 0.257 means that if firm sales increases by 1%, CEO's salary increases by 0.257%. Okay, this is very simple. Just both are percentage changes. Here is when we plug in the real numbers. Okay, so here we have denominator is the 1% for firm's sale, and the numerator is the percentage change for CEO's salary. Okay, so the same estimation results 0.257, 0.257. The log-log form postulates a constant elasticity model, whereas the semi-log form assumes a semi-elastic model. What does it mean? Let me add the page. What does it mean? Should be here. Okay, think about it and let me summarize. Log, okay, log, constant elasticity, but for semi-log, it's a semi-elasticity model. Let me summarize. We have three forms, right? Three different models, and we have the formula. And what does beta 1 hat mean? And how we call them? How we call it? So for the linear one, the formula y equal beta 0 plus beta 1 x. This means one more unit of x will causes how many units of y. Okay, so it's plus beta 1 hat units y. There's no name for this, okay? Just unit and the unit change for the semi-log. It's like log y equal beta 0 plus beta 1x. Okay, this means one more unit of x, okay? Because we didn't take log for the x, okay? One more unit of x, okay? And the beta 1 is plus beta 1 hat, but you need to time 100%, okay? So y will change beta 1 hat plus 100% y. And we call this one semi-elasticity. The last one, log. So the form is log y equal beta 0 plus beta 1 log x. Okay, we take log x and y. This means that if x is increased by 1%, okay, how many percentage will y changes, okay? Of y. Y it's always positive here. Because in our model here, it's positive, right? We'll assume it's positive, okay? But be careful about semi-log, okay? This is semi-elasticity. This is constant elasticity. I hope it's helpful for you to understand those three models. Okay, so let's see what we've covered so far, okay? Let me just write a short summary. What we've covered so far. What is the topic? Let me help you. And what is the key idea? So first, you learned what is simple linear regression, the model, okay? Which is y equal beta 0 plus beta 1x plus mu. And how we interpret beta 1? It means change in y per 1 unit of x, okay? Next one, we talked a lot about the error term, right? Mu. It means everything we can't measure, okay? It means everything we can't measure. And also, if we want to talk about the causality, the causation condition, we need the condition which is the expectation of mu given x equal 0. And this is very important. Okay, this is very important. And then we talked about r squared. It means percentage of variation in y explained by x. And then we talk about the linear model, the semi-log model, and the log-log models, okay? So we call it log models. If you use the log transformation for your data, of course, it's gonna change the interpretation to percentage or elasticity, right? Change interpretation to percentage or elasticity. Okay, this is what we've learned so far. And let's continue. The expected value and variance of the OLS estimator. Okay, the estimated regression coefficients are random variables because they are calculated from a random sample. So take a look at here. Beta 1 hat equal the summation of xi minus x bar times yi minus y bar divided by the summation of xi minus x bar squared, okay? And beta hat 0 equal y bar minus beta 1 hat x bar. Those are the formula for OLS estimator that I showed you before. And for bachelor level, we don't ask you guys to derive it, okay, to prove it, how we get it, okay? Just try to get familiar with those two formulas, okay? This is the formula of OLS estimators. And XIYI, this is our data, this is our sample, and Y bar, X bar, okay, depends on our data, depends on the sample, okay? So data is random and depends on particular sample that has been drawn from the population. The question is what the estimators will estimate on average and how large their variability in repeated sample is, okay? So here, on average means the expectation, okay? On average means expectation, and variability means the variance, okay? Let me explain you in a simple version. Think about when you shoot a gun, but don't really do that, okay? Just suppose. But actually, in Thailand, you can go to the shooting range and you pay the money and you can experience how they shoot a gun. The question, okay, you have to ask two questions. The first question, okay, the expectation of beta 1 hat equal what? It means that is OLS aiming at the right target, okay? Okay, when you shoot a gun, if we want to know the expectation, we ask, is OLS aiming the right target? How about variance? Variance means are the shots tightly grounded or all over the place, okay? It's about variability. Are the shots tightly grounded or all over the place, okay, spread out? This is the meaning of expectation and variance in terms of OLS, okay? Of course, we want both to be good, okay? The expectation and also the variance, okay? If the expectation is good, we call it unbiased. Unbiased, which means you got the right target. And if, of course, for the variance, we want it to be as low as possible, okay? Low variance means consistent shorts, okay? Every time you short, your shorts tightly grounded at the center. Okay, so low variance means consistent shorts. Together, that's what makes OLS trustworthy, okay? The first one, expectation, means unbiased. The second one, low variance, means consistent, okay? Together, they make OLS trustworthy. This is why we care about expected value and variance, okay? Expected value and variance. We can never collect every possible sample, okay? We only get one data set in real life, okay? So I'm gonna repeat it again. This is very important. In practical, we can never collect every possible sample. We only get one dataset in real life. So we need to know, is our method reliable in principle? The expected value and variance answer exactly that question, okay? Next one is about the standard assumptions for the linear regression models, okay? Those are assumptions just like the basic assumptions in economics, right? Ceteris paribus, people are rational. Those are the basic assumptions in economics. So here in econometrics, we also have the standard assumptions, okay? The first one, SLR means simple linear regression, which is here. Okay, simple linear regression. The first one, the first assumption, linear in parameters. Okay, linear in parameters. In the population, the relationship between y and x is linear. Okay, be careful here. Linear in parameters. Okay, so beta 1 should be linear. Second assumption, random sampling. I think I mentioned this one many times, okay? Random sampling, the data is a random sample drawn from the population. Each data point therefore follows the population equation, okay? Let's have a discussion of random sampling. Suppose we want to find the relationship between wage and education. So the population consists, for example, of all workers of country A. In the population, a linear relationship between wage or log wages and years of education holds. And then we're going to draw completely randomly a worker from the population. The wage and the years of education of the worker drawing are random again because one doesn't know beforehand which worker is drawing. Okay, must be random. Throw back worker into population and repeat random draw n times. So the wages and years of education of the sampled workers are used to estimate the linear relationship between wages and education. Okay, this is the idea about random sampling. So let's see the graph here. Here is our population regression function. We talked about this one before, okay? Expected y given x equal beta 0 plus beta 1x. And here we have, suppose this data point, we have the value drawn from the ith workers, okay? Xi yi here. And we have, because this is our data point and this is the PRF, so there's a gap, which is the deviation, okay? This implied deviation from the population relationship from the ith worker. As before, the gap or the deviation mu I equal yi minus beta 0 minus beta 1 xi, because yi equal beta 0 plus beta 1 xi plus mu I. And then you just isolate mu I. Okay, you're gonna get this equation. Let's continue the assumption. The next assumption is sample variation in the explanatory variables. What does it mean? It means that the values of the explanatory variables are not all the same. Otherwise, it would be impossible to study how different values of the explanatory variables lead to different values of the dependent variable, okay? So be careful here. That means we need x as different as possible, okay? Explanatory variables are not all the same. This is called sample variation in the explanatory variables. In mathematical way, we need this one, okay? Summation of xi minus x bar, square of it become positive. Or we can call this one, this assumption, no perfect collinearity, which means no correlation between x. Or in matrix form, we need rank of x equal k, which is full rank. Okay, we need rank of x to be full rank. In other words, in the sample and also in the population, none of the independent variables is constant, and there are no exact linear relationships among the independent variables, okay? Assumption SLR.4, which is zero conditional mean. Actually, we saw this assumption before, okay? It means the value of the explanatory variables must contain no information about the mean of the unobserved factor, or x and mu are uncorrelated, okay? This assumption. Under assumption 1 to assumption 4, we have this theorem, okay? Theorem 2.1, which means unbiasedness of OLS. In mathematical way, we can show that the expected beta 0 hat equal the true beta 0, and the expected beta 1 hat equal the true beta 1, okay? Let's see the interpretation of unbiasedness. The estimated coefficients may be smaller or larger depending on the sample that is the result of a random draw. However, on average, there will be equal to the values that characterize the true relationship between y and x in the population. On average means if sampling was repeated, like if drawing the random sample and doing the estimation was repeated many times, in a given sample, estimates may differ considerably from the true values. Let me help you guys. So unbiased means on average. Our estimate hits the true value. Okay, unbiasedness means that on average, our estimate hits the true value. Let me add the page because this is the very important theorem in econometrics. Okay, this is the one of the most important theorems in econometrics. So let's understand what it's saying. Okay, so on average, our estimate hits the true value. So let me write it down. The expected beta 0 hat equal the true beta 0, and the expected beta 1 hat equal the true beta 1. So it means if you took many different samples and run OLS each time, the average of all your beta 1 hat and beta 0 hat estimates would equal the true beta 1. Okay, it means if you take many different samples and run OLS each time, the average of all your beta 1 hat or beta 0 hat estimates would equal the true beta 1 or beta 0. So there's no systematic overestimate, no systematic underestimate, okay? No overestimate, no underestimate. You're centered on the truth. Let me help you summarize the 4 assumptions, okay? Assumption SLR1. What does it mean? What is the name of assumption 1? Linear in parameters. Okay. In plain English, it means this model is y equal beta 0 plus beta 1 x plus mu. And the second one is SLR12, random sampling. It means that data is randomly collected. Okay, there's no cherry picking. Next one, sample variation in X. It means that X must not be the same value for everyone. It means X must not be the same value for everyone. Next one, zero conditional mean. It means that the expected value of mu given X equals 0. Okay, so X and mu are unrelated. Okay, those are the 4 assumptions. Break any one of these, OLS may become biased, okay? That means beta 1 hat is no longer trustworthy. And among those 4 assumptions, which assumption is hardest to satisfy? What do you think? Which one is the hardest one to satisfy? Of course, this one. Okay, the SLR assumption 4, okay? Zero conditional mean, as we discussed before. For example, if you remember the education and intelligence, they are related. That means the expectation of mu given X doesn't equal 0, which means beta 1 hat, we cannot say it's purely causation, or beta 1 hat is biased. Okay, let me write it down. This assumption hardest to satisfy. Okay, for example, education and intelligence. They are related. Okay, and education is content in mu. So that means this condition doesn't equal 0, which means beta 1 hat is biased. This is why in later chapters we learn tools to fix this, okay? We use multiple regression, instrumental variable, etc. to fix this problem. Let me summarize. OLS is unbiased, but only when all 4 assumptions hold. The most dangerous one to violate is SLR point 4, which is zero conditional mean. Let's see the variance of the OLS estimate, okay? Depending on the sample, the estimates will be nearer or farther away from the true population values. How far can we expect our estimates to be away from the true population values on average, okay? This is the sampling variability. Sampling variability is measured by the estimator's variance, which is variance of beta 0 hat and variance of beta 1 hat. And next one, we're gonna learn a new assumption and a very known word, which is homoscedasticity. Okay, listen again. Homoscedasticity. What does homo mean? It just means something the same, okay? So don't panic about the word, okay? The idea is simple. It means that the variance of mu I given xi equals sigma square. This is sigma square, okay? The value of the explanatory variable must contain no information about the variability of the unobserved factor. In other words, no matter what value x takes, the unpredictable part of y is always equally wild. Okay, let me write it down. No matter what value x takes, the unpredictable part of y, which is what? The unpredictable part of y, which is our mu, right? Is always equally wild. Okay, let's take a look at the diagram. Okay, so there are three curves at x1, x2, and x3, okay? We have those three curves, and the variability of the unobserved influences does not depend on values of the explanatory variables, okay? Explanatory variables means x. And this is our population regression function, right? And see, each curve equals the spread of y value for people with that x. Each curve means the spread of y values for people with that x. Okay, for x1 we have here, x2 here, x3 here. So we can see that all three curves are the same size and shape, right? This is very important, so let me go through it slowly. All three curves are the same size and shape. So it means that the spread of mu does not change as x changes, okay? In other words, the spread of mu does not change as x changes. Okay, so this means that the spread of mu does not change as x changes. Okay, this is homoscedasticity, means equal spread everywhere. equal spread everywhere. Or whether you have low education or high education, the randomness in your wage is roughly the same size, because for x1 we have the same variation, for x2 we have the same variation, and so thus for x3 we have the same variation here. So the mu is always equally noise, okay, regardless of x, which is here. So why does this matter? Okay, why we need to learn it? Remember, this comes from the assumption SLR5, homoscedasticity. We need it because we need it for OLS to be the best estimator, not just unbiased. Remember, unbiased? We need OLS to be the best one. We need it to be unbiased and also most efficient. We'll see what happens when it's violated, okay? If this one is violated, we call it heteroscedasticity. Coming soon, okay? So let's see it. So here is the example of heteroscedasticity. Hetero means something different, okay? Hetero. So remember the last slide, homoscedasticity, equal spread everywhere. So now look at this diagram, something is different, okay? Look at the three curves. At 8, 12, and 16 years of education, okay? You see here, 8 years, the spread of wage, okay? This is, okay, so here means what? The spread of y, but y here is what? Is wage, okay? Year wage. So let's see. At 8 years, the spread is narrow. At 12, it's medium. At 16, it's wild. Sorry, it's wide, okay? Not wild. It's wide. As we can see that the curves get wider and wider as education increases, right? As education increases, the curves get wider and wider. This is heteroscedasticity, okay? The spread of mu is not constant. It grows with x. Let me write it down. It means the spread of mu is not constant. Okay, the spread of mu is not constant. It grows with x. Remember this graph? The spread of mu is constant, right? The same, the same, the same. That's why we call it homoscedasticity. But here, the spread of mu is not constant. We call it heteroscedasticity. Next one. We know OLS is unbiased. It hits the true value on average, but how consistent it is, okay? Consistent. How much does beta 1 hat jump around from sample to sample? That's what variance tells us, okay? Variance of the OLS estimator. Let's see the formula. So under assumptions 1 to 5, we have the variance for beta 1 hat and variance for beta 0 hat. look like this. In general, okay, we have sigma square in the numerator and SSTX in the denominator, okay? So let's see each of them. For sigma square, what is sigma square? It's the variance of mu, right? This is our variance of mu. It means how noisy the word is. Okay, how noisy the world is that we cannot explain, we cannot observe by the error term. And then SST X, which means how much X varies in our data. Okay, how much X varies in our data. Of course, if sigma square is larger, that means larger variance of beta 1 hat, okay? In other words, because sigma square is in the numerator, which means if the word is very noisy, mu is huge and unpredictable, our estimate beta 1 hat jumps around a lot, okay? Variability. More noise in mu, harder to pin down the true beta 1. Okay, this means less prices estimate. Another side, look at the denominator. If SST is large, that means we have smaller variance of beta 1 hat, right? Because SST is in the denominator. So if X varies a lot in our data, our estimate is more precise. More variation in X, more data, easier to see the relationship. This is more stable estimate, okay? So in general, we want sigma square, which is the noise from the mu, as small as possible, right? And then in order to get the variance smaller. But for SST, we want more variation in X, so we need it as large as possible, okay? See, the sampling variability of the estimated regression coefficients will be the higher if the larger the variability of the unobserved factors, okay? Which means if the larger the variability of the unobserved factors, which is mu, and also the variability, so variance of mu equals sigma square. If this one is higher, our variance, okay, sampling variance will be higher. Like this, okay? If sigma square is larger, so we're gonna have sampling variability, which is variance of beta 1 or beta 0. It's all our estimates, right? So if variance of mu equals sigma square is higher, that means our variance of the beta 1 hat will be larger, will be higher. But if we have a larger SST, okay, which is here, the higher the variation in the explanatory variable, which means larger SST, okay? Okay, the larger SST. So if SST is larger, we're gonna have the smaller variance, right? Okay, we're gonna have the smaller variance of beta 1 hat, or the variance of beta 1 hat is smaller. Okay, this is the conclusion. And another point, for variance of beta 0, we have extra part, which is in the numerator here, okay, which is the summation of xi squared over n. This is roughly the average of x squared, okay? This means how far x values are from 0. Let's move on. So this slide showed you that how we calculate the variance of beta 1 hat and the variance of beta 0 hat. Next one, because we need to know sigma square, right? The variance of mu, but that means we need to know what is sigma square, the variance of mu. But we don't know it, so we need to calculate it, okay? Here, this is the variance of mu, sigma square. The variance of mu does not depend on x, okay? Like equal to the unconditional variance, okay? So we just take the conditional on x out. So we get this one, variance of mu. But do you remember mu is unobservable? Okay, mu is unobservable. So how do we estimate sigma square? The question is, okay, how do we estimate sigma square? Because mu is the error term. I mentioned you before, mu is unobservable. It's the error term that we couldn't catch. So how do we estimate sigma square? Let's see the step. Step 1, what is mu? What is sigma square? Okay, so sigma square is, this is the first step. Sigma square is the variance of mu, okay, from homoscedasticity. The variance of mu is the same everywhere, just one number, sigma square. Okay, it's constant because homoscedasticity, so it's constant. So we can't see mu directly, but we can see the residual, right? We can't see mu, but we can see the residuals mu I hat. Mu cannot, but we can see from the residuals, right? Residual mu hat. So we're gonna use mu hat, and then, okay, this is the mu hat. This is step 2. This is our first attempt, okay? First try. So we use the mu I hat minus mu I hat bar, okay, minus the average, and then we square it. We take the sum, and then we divide it by n. This means just average the squared residual, okay? This is just average the squared residual. One could estimate the variance of the errors by calculating the variance of the residual in the sample. Unfortunately, this estimate would be biased. This sounds okay, average the squared residuals. This sounds reasonable, but this is biased. It systematically underestimates sigma square. Why? Because OLS already minimized the residuals, right? Remember OLS, we try to minimize the residuals. It made them as small as possible. So the residuals are slightly too small compared to the true mu. That's why we have our next step. Step 3, which is the fix. Okay, we instead of dividing by n, we divide it by n minus 2 instead of n. Okay, so here the same, just different denominators. At this step, we divide it by n, but this step, we divide it by n minus 2. Why 2? Why we subtract 2 from the denominator? And now it's unbiased, okay? An unbiased estimator of the error variance can be obtained by subtracting the number of estimated regression coefficients from the number of observations, okay? Number of observations means n, number of the estimated regression coefficients, which is 2. Why we have 2? Because we have beta 0 hat and beta 1 hat, okay? Why 2? Okay, so here y2, y2. Because we estimated 2 parameters, right? Which is beta 0 hat, beta 1 hat, okay, which used up 2 degrees of freedom. Okay, you must learn this degree of freedom in your statistics, okay? So we subtract 2. Let me help you with the summary. Okay, we have the formula. The first one is 1 over n times summation mu hat squared. And this we divide it by n. And this is biased or not? This is biased, right? Too small. And next one, we have 1 over n minus 2 times the summation mu hat squared. And then we divide it by n minus 2. And this is unbiased, okay? We estimate sigma square using residuals, but divide it by n minus 2, not n, because we already used the data to estimate two parameters, which is beta 0 hat and beta 1 hat. This gives us an unbiased estimate. Okay, almost done. Here is our last slide of this chapter. So please bear in mind and please follow me. So this slide ties everything together. Under assumption 1 to 5, the expectation of sigma square hat equal the true sigma square. This means unbiasedness of the error variance, okay? And also this is our formula from the last slide. We divide it by n minus 2 here, okay? Here, we divide it, let me copy it. Okay, we divide it by n minus 2 is confirmed unbiased. On average, it gives the true sigma square, and we require assumption 1 through assumption 5, okay? All 5 assumptions. Next one, stand errors, okay? Calculation of stand errors for regression coefficients. We have variance of beta 1 hat, but sigma square is unknown, okay? Sigma square is unknown. That's why we plug in sigma square hat instead. That's why we have our sigma square hat here, and also for beta 0 hat, we have sigma square hat there. Okay, we plug in sigma square hat for the unknown sigma square. And if we want to get the standard error, we just square root the variance, okay? The estimated standard deviations of the regression coefficients are called stand errors. They measure how precisely the regression coefficients are estimated. What is standard error? Let me help you. What is standard error? Stand error means estimated stand deviation of our estimate. Okay, this is the meaning of stand error. It tells us how much does beta 1 hat typically jump around from sample to sample. Of course, we want small stand error, okay? We want small stand error. Okay, so SE, normally we use this one. This is stand error and the meaning. If it's small, here I'm gonna use beta 1 hat. But beta 0 hat actually is the same, okay? If the SE of beta 1 hat is small, that means beta 1 hat is precise. Okay, which means stable across samples. Another one is large SE of beta 1 hat, which means beta 1 hat is imprecise. So it jumps around a lot. Stand error equals how reliable is our measuring tool. Which is OLS. Why do we care, okay? Why do we care stand errors? Because stand errors are used for everything that comes next, okay? We need stand errors for the first one, hypothesis testing. For example, is beta 1 hat significantly different from 0? Okay. And next one, we need stand error for confidence intervals. We learned this one from statistics, okay? For example, what is the range of plausible values for beta 1? What is the range of plausible values for beta 1? If no stand error, no inference, and also if no inference, no conclusion. Okay, I think that's done. I'm done from my part. A lot of information here, and I'm gonna summarize chapter 1.2 later. Okay, let me write it. Okay, so I'm gonna summarize chapter 1.2 later, which means I'm gonna do it next Monday, okay, in the classroom. So I'll see you guys next Monday. Please review it. I know it's a lot of information, a lot of assumptions, right? A lot of formulas, but please review it. Just get familiar with it, okay? Otherwise, you will feel it's too difficult and too hard. Okay, so I'm done from my part. So see you. Bye bye.